Alrighty, we're back at it. This is 5.6, Radical Expressions and Exponents. And we're going to be dealing with properties of radicals and exponents. The joke is, how is an artificial tree like the fourth root of negative 68? Neither has real roots. And you'll understand that the fourth root of negative 68 has no real roots as well. You're going to learn what an index is and what a rational exponent is. Okay. So, the nth root of A is basically whatever number you're taking the root of A is. So we write this like nth root of A. And so I'll use numbers. So let's say we had the square root of 4. Well, our n would be represented by 2. And of course, we don't normally write square root with a 2 there. We just know that it's the square root. And so the square root of 4 is then 2. Another example would be, and there's tons of them, would be the third root of 8. In this case, we're taking the third root, so we do write a 3 there. And the third root of 8 is also 2. And we'll be taking fourth roots, sixth roots. You can take any number like that. And so it's written in this form here, and the n is what is known as the index number. Index number. That's some vocab. And the a, this number that you're taking the root of, is known as the radicand. Okay, and there's some different cases that you're going to need to know. So I'll make a new screen here. And there's some different cases. So I'll make this table. This is roots. So the first case, let's say you have an even, or let's say for the first one, you have an odd index number. So you're taking like the third root. In that case, you're only going to have one real root. Okay, and an example of this, I'll put examples over here, would be if you take the third root of negative 8, that's going to be negative 2. Negative 2 times negative 2 times negative 2 is negative 8. So when you take the third root of negative 8, you're going to get negative 2. And that's only one real root. So let's say you have an even index number, and your radicand, your A, is positive. In that case, you are going to have two real roots. So an example of this would be is if you take the square root of 4, it's going to equal plus or minus 2. Right? You remember that. If you take, so that's an even n, right? We took the square root and our a was positive, so we'd have plus or minus 2. Another example would be if you were to take the fourth root of 16, your answer would then be plus or minus 2. Our n is even and our a is positive, so we have two real roots. Okay, what if our n is even? we have an even index, and our radicand is negative. Negative. In that case, can we take the square root of a negative number? No, we can't. That's how we get imaginary numbers. So in this case, you're going to have no real roots. An example of this would be if you were to take the square root of negative 16. You can't take the square root of a negative number, so there's no real roots. Okay. And then the last case is if you have a radicand, or A, of 0. And in that case, you're going to have one root, but it's going to be 0. One root of 0. Example is if you take the square root of 0, you get 0. If you take the third root of 0, you get 0. Okay, those are the different cases. Oh, and another thing that I wanted to mention is another way of writing these roots. Say for instance you have the third root of 4. Another way of writing that is 4 raised to the 1/3. And we've touched on this before. So it's 1 over the root, written as an exponent. Another example would be if you take the square root of 16, it's 16 to the 1/2, 16 to the 1/2, it's the same thing. Let's see, is there anything else I wanted to mention before we get going? Oh, if it asks for you to find all real roots, find all real roots. If it doesn't specify that, you can assume that it wants the principal root. And what that is the positive one. So if it wants the principal root of fourth root of 16, you would just write 2. You wouldn't write plus or minus. Okay. All right. So this wants us to find all the real roots. So if it's going to be a even root and a positive radicand, an even index or a positive radicand, then we have to do plus or minus. So it wants to find out the fourth root of 81. And in that case, it's going to be plus or minus 3, right? If we took positive 3 and multiplied it to itself 4 times, we get 81. If we took negative 3 and multiplied it to itself 4 times, we would get 81. For this one, the cube root of negative 125 is going to be negative 5. If we multiplied negative 5 by itself 3 times, negative 5 times negative 5 is 25. 25 times negative 5 is going to be negative 125. So our answer is negative 5. This one, we've got the 6th root of negative 729. That's a big number, but don't panic because we have an even index and an odd radicand. Or not an odd, a negative radicand. We're trying to take the 6th root of a negative number. There's no real roots. No real roots because it's taking the even root of a negative. Okay, try these ones by yourself and I will supply the answers. Okay, this one is no real roots. This one is going to be plus or minus 1. And this one is going to be 5. And you would write that as cube root of 125 equals 5. Okay, some properties for you. Let's see. So this is just giving you examples. Really what you need to know is over here. And it's saying that if you have, if you're taking the root of two different variables, like an a times a b, you can break it into the root of a times the root of the root times b. So an example would be is if you're taking the square root of, let's go with 16, you can break that into the square root of 4 times the square root of 4. Because 4 times 4 is 16. 16 breaks into 4 times 4. So then you can take square root of 4 times square root of 4. And there you go. This one says that if you have the square root of a fraction or a quotient, like the square root of 9 over 4, what you can do is break that into two different roots. So the square root of 9 over the square root of 4, right? It's the same thing. And then you can evaluate it from there. Square root of 9 is 3. Square root of 4 is 2. Bada bang. Okay, now we're going to get a chance to use those properties. So, what we have here, and I'll rewrite this bigger, is the third root of 27 times x to the 6th. So using those properties we just talked about, I can break this into two different terms. So I'll break it into the third root of 27 times the third root of x to the 6th. Now the third root of 27 is 3, I already know that. So I'll go ahead and write that. And then I'm going to rewrite this in rational exponent form. So remember that I said you can rewrite radicals as exponents, right? If you have the third root, it's the same as writing it as 1 raised to the 1/3. So I'll do that. 3, because I got 3 from that, times x to the 6th, and then all of that is raised to the 1/3. Okay, now I got to figure out what to do with this mess here. And if you can remember, if you have, with properties of exponents, if you have an exponent raised again to the exponent, they multiply. So this becomes 3 times x, and then 6 times 1/3 is 6/3. So 3 times x to the 6/3. 6 divided by 3 is 2, so this is going to be 3x squared. I really write slanty. I apologize for that. This board needs to be taller for me, I guess. Okay, this one, we've got the third root of x to the 3rd over 7. So I'm going to do the same thing. I'm going to break it into two roots. So we've got the third root of x to the 3rd over the third root of 7. Okay? So I can rewrite this one as a rational exponent, and it's going to be x to the 3rd raised to the 1/3, okay, over third root of 7. And then 3 times 1/3 is just going to be 1, so this simplifies to x, and I've got x over the third root of 7. And now we're not done, because if you remember, we can't have a radical in the denominator. Okay? I don't know if I told you this story before in class, but back in the 60s, when my parents were alive, there were a lot of hippies around, and they were known as radical people. And if you let them into your basement, bad things would probably happen. So you don't want any hippies in your basement, okay? You don't want any radicals in the denominator. That's a way for you to remember that. We got to get it out of there. So what we have to do is, since it's the third root, we have to multiply the top and bottom by 2 more third roots of 7. So I went to parentheses actually. So I'll multiply this by the third root of 7 and then another third root of 7, so that there's 3 of them. Third root of 7 times third root of 7 times third root of 7 is going to be 7. So that'll get rid of the radical. And then I need 2 more on top to even it out. Third root of 7, third root of 7. So now my denominator, all of these multiplied together, equals 7. And on the top, I've got third root of 7 times third root of 7. So that's going to be third root of 49 all over 7. And we can't simplify this anymore, so that's our final answer. Okay, these are for you to try on your own. But I need to talk about this first one very quickly. So this is the fourth root of 16 times x to the 4. And in this case, I would break it up into the fourth root of 16 times the fourth root of x to the 4th. Fourth root of 16 is 2. And the fourth root of x to the 4, you might already be doing that in your head, is going to be x. But it's actually the absolute value of x. And it doesn't say this in the book, but it should. And the reason for that is if I take a negative number, like a -1, and I plug it in here for my x to the 4th, so let's see, I'll do this in blue, and I plug in -1, and that's to the 4th, and then the 4th root. That's going to be -1 times -1 times -1 times -1. So that's going to evaluate to a positive 1. Okay, and you take the 4th root of positive 1, it's going to be 1. So even if you plug in a negative number, the answer is going to be positive. So this would already be absolute value. Okay, and then the answer for number 2b, I'll go ahead and do this really quick. So I'll split it into 2. We've got 4th root of 8 over the 4th root of 3. Okay, and then this simplifies to x squared over 4th root of 3. So then I need to multiply the top and the bottom by 4th root of 3 more times to get 4 on the bottom. So when I do that, it's going to be x squared times 4th root of 3 times 4th root of 3 times, again, 4th root of 3 on the top, and then it's just going to be 3 on the bottom. And then these 3 multiply together, and I'm going to have x squared times the 4th root of 27 all over 3. And that's my final answer for that one. And then this one here, I'll rewrite these in rational exponent form. So I've got x to the 7/3 times x to the 2/3. Actually, you know that we're going to learn about this a little bit later in the chapter, so I'll do it a different way. You totally could do it that way, but I'll do it a different way. So we learned about how you can, if you've got 2 variables under the same root, you can break them into 2. But you can also, if you have 2 variables of the same root, you can combine them to be underneath the same root. So in this case, we'll have the 3rd root of x to the 7th times x squared, which is going to be the 3rd root of x to the 9th. Alrighty. And that's going to evaluate to x to the 9/3 because I'm writing, stay with me here. I'm writing this as x raised to the 9th, and then the third root is going to be x to the 9/3. And then 9 divided by 3 is 3, so your answer is x cubed. Okay, more properties for you. This one we already talked about. It's basically saying that you can rewrite the square root of x as x to the 1/2, or you can rewrite the third root of x squared as what? X to the 2/3. So we already talked about that. This one says that we can take, if we have a root and we have an exponent, we can do those, we can interchange the order of which we do those, basically, is what it's saying. So if we have like x squared to the third root, that's the same as x to the third root and then all of that squared. It's the same thing. Here I've got my exponent on the inside of my radical, here I've got it on the outside of my radical, but you're going to end up getting the same answer. So we'll do a couple of those. So this is asking us to write the expression negative 125 raised to the 2/3 in radical form and then simplify. So if it's a big number, I always like to take the root first as opposed to the exponent first. So let's do that. Let's write negative 125, and then we're taking the third root, and then we're going to square it. So if we take the third root of negative 125, we're going to get negative 5. Okay, that's all on the inside of my parentheses. And then if we square negative 5 squared is going to be equal to 25. And like I was saying, I like to do the root first. We could do it the other way, but let me show you what you would get. If you would have done it the other way, you would have gotten negative 125 squared, and then all of that, take the third root of all of that, and then you would have to square negative 125, and you get this huge number, and you have to take the third root of that. And if you have a calculator, you can do it. You'll still get 25, but I like to do it this way so you can do it in my head. So these are for you to try on your own, and then I will tell you the answers. So this one is the third root of 64. Wants you to write it in radical form, and that's radical form, but then we can just go ahead and evaluate that. And the third root of 64 is 4. Excuse me. This one, you can write it as the square root of 4 raised to the 5th. And if you were to evaluate that, you would get 2 to the 5th, and 2 to the 5th is 32. And then this one, you could write it as the fourth root of 625 and all of that cubed. Fourth root of 625 is 5. 5 cubed is 125. Okay, so now it gives us radical form. So it starts out with radical form, and it wants us to write it using rational exponents. So for this one, you've got the fourth root of 7 cubed, so you can write this as 7 to the fourth root. Let's see, actually, you always have to do the inside first. So you write this as 7 cubed raised to the 1/4, because you're taking the 4th root of it, and raised to the 1/4 is the same. And then you can just multiply these exponents, and you'll get 7 to the 3/4. And if you knew that already, with skipping this step, I usually skip this step, but I'm showing you now. And we can't evaluate, this doesn't evaluate to anything simple, so we can leave it like this. My pencil is, anyway, that's 7 to the 3/4 if you didn't know. Okay, in this one, we can rewrite this as 11 to the 6th raised to the 1/3, and then we multiply these exponents and we get 11 to the 6/3. And what is 6 divided by 3? 11 squared. And we already know that 11 times 11 is 121. So that one was easier to evaluate. Okay, and these are for you to try on your own, and then I'll tell you the answers. This one, 4th root of 81 is 3. We've got 3 to the 3rd, and that equals 27. This one, you can rewrite it as 10 raised to the 9/3, and 9 divided by 3 is 3, so it's 10 cubed, and that is 1,000. Okay, and then this one is 5 raised to the 2/4, right? Because it's 5 squared, and then that whole thing being 4th rooted. So we put the 4 on bottom, and that can reduce to, or we can simplify that to 5 raised to the 1/2, and that's just the square root of 5. It's not a easy number to write, so we can leave it like that. Okay, I'm not going to spend any time talking about this. This is all properties of exponents, and we've gone over this a lot, but you should already have this committed to memory. It's how exponents can add together, multiply, subtract, divide, that sort of thing. Okay. Now we're going to use those handy dandy properties. And we have 25 raised to the 3/5 times 25 raised to the 2/5. So we have 2 exponential numbers that have the same base. So that means since they're being multiplied, their exponents add together. So this becomes 25 raised to the 3/5 plus 2/5, right? They multiply, so we can just add the exponents. That's exponent property. And 3/5 plus 2/5 equals 5/5. So 5/5 is 1, so your answer is just 25. This one, we have 2 exponential numbers with the same base being divided. So in this case, our exponents subtract. So we've got 8 raised to the 1/3 minus 2/3. 1/3 minus 2/3 is negative 1/3. So we've got 8 to the negative 1/3, and we can rewrite that as 1/8 to the 3rd. 8 to the 1/3. And we already know the 3rd root of 8, that's 2, so our final answer is 1/2. Okay, try these ones on your own, and then I'll supply the answers. Alright, so this one we can add our exponents, and we get 36 raised to the 4/8, which is the same as 36 to the 1/2. So square root of 36 is 6. This one, we've got negative 8 to the negative 1/3, so that's the same as 1/8 to the 1/3. And negative 8 to the 1/3 is negative 2. So this is 1 over negative 2, or you can write it as negative 1/2. Okay? This one, we've got two exponential numbers with the same base being divided, so we subtract them. So we've got 5 raised to the 9/4 minus 1/4. And 9/4 minus 1/4 is 8/4. 8 divided by 4 is 2, so we've got 5 squared, 25 for that one. Okay. This, I believe, is the last equation. So, this is a music problem. It said frets are small metal bars positioned across the neck of a guitar so that the guitar can produce the notes of a specific scale. So these are your frets right here, these metal bars. I used to play guitar for a little bit, but I was never very good. So I don't really know exactly what it's talking about. But anyway, to find the distance a fret should be placed from the bridge. So the bridge is this thing right here. And they want to know what distance away from this the fret should be placed. You got to multiply the length of the string, which looks like the length of the string is 64 centimeters, by 2 raised to the negative n over 12, where n is the number of notes higher than the string's root note. Okay, so I guess the root note is something important. Where should a fret be placed to produce a G note on the E string? Okay, and good thing it tells us, because I wouldn't know that. G is 3 notes higher than the root note. Okay, so our equation is length of string times 2 raised to the negative n over 12. It doesn't have that written out for us, but it just tells us to multiply the length by that, so that's what I did. And then we want to plug in 3 for our n and 64 for our length. So this is going to be 64 times 2 to the negative 3/12. Alrighty? So I'm going to go ahead and simplify this fraction. Negative 3/12 can simplify to negative 1/4. So this is going to be 64 times 2 to the negative 1/4. And 2 to the negative 1/4 is the same as 1 over 2 to the 1/4. So I'm going to rewrite this as 64 over 2 to the 1/4. Okay, and this is where I need my calculator. So I'm going to just go ahead and type this whole thing into my calculator as is. And whenever you do this, whenever you're using rational exponents, always put parentheses around them. So what it's going to look like is 64 divided by 2 raised to the 1/4. So this is what it's going to look like. Hope you can see that shadow. We got a shadow going on. See, I've got the parentheses around my 1/4 there, and then this is all one thing. The calculator knows that, and I'm going to evaluate it. And it's 53.8. Does it want us to round? We'll just round to the nearest tenth. So we've got 53.8, and we're in centimeters. Cool. So our whole length is 64, and this is less, so we know that that's good. If it was more than 64, we know that our fret would be way up here, and that would be wrong. And maybe some of you music people out there know what it's talking about with the G note on the E string. Anyway. Okay, we'll not do that, and that's the quiz. So, okay, we'll be done. See you in class.